This is the example that I did in class. I'm going to do it again. I'll do it in two different ways. There's actually two ways to do it. I'll start with perhaps what's the hardest way, but it's the more complete. We are given a transfer function. So this transfer function is a x over f, and it's a polynomial. It's a ratio of polynomials, actually. We'll be dealing with transfer functions later, but in general, a transfer function will basically relate the input, which is a force, to the output, which is a displacement. Now, the denominator of this transfer function is your mass spring damper system, and we'll see this over and over in this class. So just by looking at that denominator, you should know that the mass is 5 kilograms, the damping coefficient is 20 newtons second per meter, and the spring constant is 25. The numerator, normally you want that to be 1. It's not 1, it's 3, and so it's going to be, there's going to be some caveats to it. We'll deal with it. Worst case scenario, that numerator could actually be a polynomial in and of itself, so it could be 3s plus 1, for example, and that would be even more complex. So anyway, let's solve this. We got to find the steady state displacement. So, well, for one, we know, I'm going to write this down here. So the solution, so when you do these problems, the first thing you got to realize is the solution is going to have this form. Displacement as a function of time. It's going to be some amplitude, which is a function of frequency, times a sine function, omega t, plus phi, which is also, this is your phase angle, also a function of frequency. So basically the two things we need to find are this x and this phi, right? The amplitude and the phase angle. We also saw in the notes Thursday, that this amplitude omega is actually going to be a multiplication of your magnitude ratio times the force, the amplitude of the force. So again, go through the notes, and we define this magnitude ratio precisely to give us this magnitude of the force as it relates to the magnitude of the displacement. That's why it's called the magnitude ratio. So since our force input is a harmonic, meaning it's a sine, we know also from the notes, and you should know this, that the magnitude ratio, when you have a harmonic force, is going to be basically the absolute value of your transfer function evaluated at this particular time. This is, by the way, called the frequency transfer function. And when you take the magnitude of the frequency transfer function, you get your magnitude ratio. And then you go back to this equation, and then you can solve it. Anyway, so we're going to evaluate our transfer function when s is equal to I omega, and we'll find the magnitude of that. Oh, by the way, we also know that phi is actually going to be the angle of our frequency transfer function. So these are the two things that you need to know to be able to solve this problem with the transfer function method, right? The frequency transfer function, T I omega, which is a new concept, and we're going to be using it quite a bit. The frequency transfer function can have a magnitude and an angle, and that gives you precisely your magnitude ratio and your phase. So let's find the magnitude ratio first. So this magnitude ratio, which is going to be T I omega, absolute value, is going to be basically the amplitude of this transfer function evaluated at I omega. So it's going to be 3 divided by, and it's going to be 5 times I omega squared plus 20 times I omega plus 20. Oops, what did I just do here? Let me just zoom out. Plus 25. The amplitude of that. And by the way, we know that omega is 7 radians per second. That comes right from here, right? And so let's plug all that in. So T I omega magnitude is basically going to be the magnitude of 3 divided by okay, so I'm just going to do it out, but you should be able to do this math. I is the square root of minus 1, so I'm going to do some algebra here. So that ends up being I'm going to skip a step, but you can do it on your own. I'm going to have something that's going to look like this: 25 minus 5 times 7 squared plus 140i. I'm basically skipping a step, but again, it's algebra, and you have that in your notes. And so, essentially, I'm eventually going to have to find the magnitude of 3 over minus 220 plus 140i. Okay, so this is my... Okay, so what's inside here, this is my frequency transfer function. So right now I'm actually trying to find the the amplitude first of that, or the magnitude, to get my magnitude ratio, and then I'm going to do the same thing with the angle. So what's the magnitude of that? So the absolute value of that, so the absolute value of this ti omega is basically going to be the amplitude or the magnitude of the numerator divided by the magnitude of the denominator. So the numerator just has a magnitude 3, the denominator has a magnitude square root of 220 squared plus 140 squared. And then eventually you do that out, and you're going to have ti omega is equal to, I think I get 0.016, which is, as we said, it is your magnitude ratio. Okay? So while we're on the magnitude ratio, we can go back to that relationship at the top, and from the magnitude ratio, now we can find our amplitude, because we know that our x omega is equal to the magnitude ratio, which is 0.016, times f naught, which is the magnitude of our input force, which is 10. You can find that from what's given, times 10. So our amplitude is 0.16. That's easy. All right. Secondly, we're going to do the angle. So the angle phi is basically going to be the angle of our frequency transfer function. I'm going to scroll back up so you can see it. There's your frequency transfer function up there. And so basically that's going to be the angle of the numerator minus the angle of the denominator. The angle of the numerator is going to be inverse tangent of, and so there's a complex number in the numerator, a complex number in the denominator. So, and the angle is going to be the inverse tangent of the imaginary part over the real part. So for the numerator, imaginary part is 0, real part is 3, minus the angle of the denominator is inverse tan of imaginary 140 divided by negative 220. But at this point, you know that you can basically get rid of this minus, and this minus will cancel out. So I know that basically my angle is going to be the inverse tangent of 140 over 220. Nice. Why can I do this? Well, it's just because of the trig property that minus tan of alpha is the same thing as tan of minus alpha. That's just in the books. Okay, so this is going to give me a first, if you take an inverse tan of a positive number, that's going to give me a first angle quadrant, but we know that our angle needs to be in either quadrant 3 or 4, and we basically need to compare m omega squared, compare it to k, so that we know which one is greater. Then we know if we're in quadrant 3 or quadrant 4. So m omega squared, when you do it out, it's going to be, 5 times 7 squared. That's going to be 245. K is given as 25. So obviously m omega squared is greater. Therefore, we are in Q3, right? So let's find this phi Q1 first. So phi Q1 is the inverse tangent of that, which is going to be 0.567 radians. So phi Q3, which is the one we actually need, is going to be pi plus that 0.567, which is equal to 3.771. Yeah. So now we're done, because now we write our answer right here. Steady state is going to be my amplitude, which I found to be 0.16 times the sine of omega t, but omega is 7, so 7t plus 3.71. I might as well put a unit there. Okay, just a quick note here. Let's go back to how we got the displacement and the angle. So we started by looking at this frequency transfer function, and if we take the magnitude of that, you get your m omega. If you get the angle of that, you get your phase. If you're savvy with your calculator, there's a way to do this in the calculator so that you input your transfer function as a complex number. So you can actually input 3 divided by minus 220 plus 140i. And there's a way to find the absolute value of that. And if you do it right, it's going to tell you exactly 0.016. And there's an angle function of that. I know you can do it with the TI-89, maybe with the TI-83. So maybe on Tuesday I'll show you guys how to do it. And it's a good way to do it so you can check your answer. Okay, that's it.